Hello everyone, I'm Mr. Furlong, and today we're talking stars. The universe is filled with stars, while even our own galaxy is made up of 100 billion stars, and there could be hundreds of billions of galaxies. That's a lot of stars. Our sun is kind of unusual as well. When we look up in the sky and we see all these points of light, we might think that there's just one star there and there's planets that are revolving around it. But many of these, there are two stars right by each other. But from our vantage point, it only looks like one point of light. These are what are known as binary stars. Our solar system only having one star is, again, a little bit unusual, which is why I can appreciate this scene in Star Wars where there were two sunsets. I think on most planets, that's probably what we would see. Now, there's a lot of things that we can determine about stars, such as their temperature, luminosity, brightness, and spectral type. So let's start with luminosity. Luminosity is the rate at which a star radiates energy. Now, we might think that it has to do with how big the star is, but it really is more about how massive the star is, how much mass is contained. The greater the mass, the greater the luminosity. So a star with a lot of mass is going to be releasing much more energy than a star that has less mass. The other is spectral type. This is the color of the star. This is also related to mass. So if the mass is greater, the star typically tends to be a little bit bluer in color. If there's less mass, it tends to be a little bit redder in color. So if we look at the color, we can also then sort of determine how much energy that it's giving off. We can look at the temperature. Temperature is measured by what that surface temperature on the star is. And absolute brightness. So this is compared to the brightness of the sun. Is it brighter than our sun, or is it dimmer than our sun? Now, how we can determine all this very easily is by using what's called a Hertzsprung-Russell diagram, or an HR diagram. So for instance, if we take our sun, which is right here, we can find out lots of different things. For instance, the temperature is right around 6,000 Kelvin. The luminosity is 1. The spectral type is G, so it's a yellow star. And the absolute brightness is about +5. But what about a nice big star? How about the star Betelgeuse, which is right here? It has a lower temperature than ours, right around 3,000 Kelvin. It has a greater luminosity, so it's radiating more energy. It's a very large star. Its overall brightness, though, is about -6. And its spectral type is M. So this is a red giant. So if you look in the wintertime, if you look in the constellation Orion, you will see that makes up the body of Orion, a red star. That's Betelgeuse. Now, not all stars are the same. They go through a specific life cycle, just kind of like a person does, right? And they change throughout that time. So stars start out in nebulas. Nebulas are just these large clouds of gas in space. And they do, because of gravity, will start to form into stars. And we're going to look at a couple of different types. The first one is what's called a main sequence star. If you look out in that HR diagram, you may have seen that. Our sun is a type of main sequence star. Many stars will go through this process where once they have formed, they start out kind of in a bluish color. They have more energy. They start releasing a lot of this energy. Our star is about halfway through its lifespan. It is now a yellow star. Eventually, it's going to become a red giant. And so the size of the star is going to be increasing, although it's losing mass and it's losing energy. Another type of smaller star is called a red dwarf star that might form in that nebula. A red dwarf eventually will become a white dwarf star, which eventually becomes a black dwarf star, at which point it's not radiating out any energy. Red giants that are larger in size will eventually explode and become a supernova. Now, these will be the very large red giants. Our sun, although when it does explode, it will probably just go nova, which is not as large of an explosion. After that explosion, it then becomes a neutron star. Now, If this star, though, was really massive, and our sun is not going to do this, but eventually it could become a black hole. Now, this process might take about 13 billion years to complete, to go through its life cycle, but eventually, as stars die out, we'll always have new stars forming. We're going to be practicing using the HR diagram, and we're going to be looking at all different types of stars in the next couple of activities, and I'll see you in class.